Ander, can we start?
Yeah, whenever you tell me that we can start.
So hello everyone, and welcome to our second extremal and probabilistic combinatorics webinar this academic year. As usual, there will be a talk for the next hour or so, followed by questions. We will have questions which are within the recorded part, which will eventually appear on YouTube and so on. But if you have any questions during the talk, you can ask them already then. There will also be questions in the unofficial part where we stop recording at the very end. Or if you have problems with your mic, you can also type any question in the chat, and I can read it out to our speaker. And so now it's my pleasure to introduce Ander Lamaison from Masaryk University in Brno, and Ander will talk about the hypergraph Turán problem. So please.
Okay, thank you. Thank you for having me here. So yes, today I was actually scheduled to give this talk at the DIMEA seminar here in Masaryk University. But since this came up, we have decided to merge it. So welcome to the crossover between the EPC DIMEA, this joint session. As the title says, I'm going to talk about hypergraph, Turán problem in hypergraphs. I am only going to talk about 3 uniform hypergraphs. The results that I'm going to present are only about 3 uniform hypergraphs, but I guess it makes sense to introduce the problem at least a bit more generally. And this is joint work with Frederik, Garbe, and Král. So the first definition, I guess it's a concept that it might sound familiar to many of you, if at least for the particular case of graphs. So if we have some k-uniform hypergraph, its Turán density is the largest value of D, such that there are arbitrarily large hypergraphs with density arbitrarily close to D and which do not contain edges of subgraph. Density being, of course, the proportion of the edges out of the possible k-tuples that are present in the hypergraph. So this is usually phrased as for a fixed number of vertices n, you take the extremal number, the maximum number of edges that you can take on n vertices without containing h. And here we are just dividing this by n choose k and taking the limit. And as I mentioned, this problem is relatively well known in the case of graphs. It is like the solution is relatively well known. Rödl and Schacht proved that for any graph, the Turán density depends only on the chromatic number. And that an asymptotically extremal construction is just to take a complete multipartite graph, which has chromatic number which is 1 less than the chromatic number of G. So that way you will never contain G. And this maximizes the number of edges that you can take with that. So for graphs, this question has been solved for 75 years. For hypergraphs, it is very much open. Even for simple cases, as in 3 uniform hypergraphs, even hypergraphs as simple as K4 or even K4 minus an edge, those cases still remain open. Still, even though they remain open, we do have upper and lower bounds, and I want to somehow suggest that we are pretty certain that these lower bounds of 5/9 and 2/7 are pretty likely to be correct. So we have some upper bounds that come from flag algebras that do not match the numbers, but they are very close and seem to suggest that, if it is going to be some rational number with small numbers, it has to be these two. But one thing that I want to mention about both these constructions and about the complete multipartite graphs is that in these constructions, the edges are very much not well distributed. So in the case of complete multipartite graphs, you have very large independent sets. You have independent sets of linear size. So can we somehow avoid that? Can the edges be well distributed? Can the hypergraph, the host hypergraph, be in a certain way pseudo-random and still have large density and avoid age at the same time? Well, that is a question that I think the first to look into this question were Rödl and Schacht because of an example that I will introduce in a second. But let's fix some definition. So we are going to say that hypergraph is the epsilon quasi-random if every epsilon proportion of the vertices, every subset with an epsilon proportion of the vertices, spans or induces a hypergraph whose density deviates from the density of the original by at most epsilon. And then the question that we are going to ask is the uniform Turán density will be the largest value of D such that we have arbitrarily large, arbitrarily quasi-random hypergraphs whose density tends to D and which do not contain H as a subgraph. So this is our main definition. So I guess if there is any question about this definition, I guess I would rather have it here while I talk about the next while I'm talking a bit about it. But I am going to tell you about this uniform Turán density that in the case of graphs, it does not make for a very compelling question because for every graph, the uniform Turán density is 0. If you have a quasi-random graph with positive density, then you contain arbitrarily large cliques. But in 3 uniform hypergraphs, that's not the case. And we have the following example that sort of, I think, motivated the question for Rödl and Schacht. So this is a construction that's due to Rödl and Schacht, and our hypergraph, the graph that we are going to forbid, is K4 minus an edge. So the 3 uniform hypergraph with 4 vertices and 3 edges. And the construction goes as follows. We take a uniformly random tournament, so the complete 2 uniform graph, and we randomly orient the edges. And for every triple of vertices, we are going to place an edge in our hypergraph if what we see there is an oriented triangle. So you can see here 3 of the edges that we will place into our hypergraph. And then to justify that we do not see H0 in this hypergraph, we can look at the pairs of vertices AB, AC, and AD. By pigeonhole, either 2 of them are oriented towards A or 2 of them are oriented away from A, and those 2 pairs of vertices cannot be in the same oriented cycle. So this construction will not contain a copy of H0. And you can see, using concentration inequalities, that with high probability, the graph that we construct is very quasi-random and the density is 1/4. So that means that the uniform Turán density of K4 minus an edge is at least 1/4. So a bit more, some other things in terms of what was known about this parameter before we came in. So Reiher, Rödl and Schacht characterized which hypergraphs have uniform Turán density 0. It is a characterization that I am going to show you later, but it makes sense to leave it for later. But their characterization implies that for every 3 uniform hypergraph, I guess this is going to be just here. Now, from this point, everything is going to be about 3 uniform. And they proved, from their characterization, it follows that for every hypergraph, either the uniform Turán density is 0, either it is vanishable, or then the uniform Turán density is at least 1/27. And they asked whether this 1/27 can be improved. So whether there exist hypergraphs with uniform Turán density equal to, or failing that, arbitrarily close to 1/27. And well, let's start looking for those hypergraphs. It makes sense that if a hypergraph exists with density equal to 1/27, that there should be some small example. So let's look on 4 vertices. Using this characterization by Reiher, Rödl and Schacht, you can see that there is, in fact, one minimal non-vanishable hypergraph on 4 vertices, which is K4 minus an edge. And we already saw in the Erdős-Heinel construction that it has uniform Turán density at least 1/4. Well, then let's go to 5 vertices. On 5 vertices, there's also one minimal non-vanishable hypergraph, which is the 5 cycle. And there is a construction for a quasi-random hypergraph with density 4/27, which misses it. So let's go to 6 vertices. On 6 vertices, using the characterization, you see that there, you can check that there are 4 minimally non-vanishable hypergraphs, and in fact, all of them have uniform Turán density at least 4/27. In fact, for each of them, one of the 2 previous constructions works for avoiding that subgraph. So at this point, the question of the 1/27 is starting to look a bit grim. Maybe it's better to go for arbitrarily close to 1/27. But thankfully, on 7 vertices, we come to an answer, and in fact, on 7 vertices there are some hypergraphs which have uniform Turán density exactly equal to 1/27. And in fact, we showed more. We proved that there exist infinitely many minimal examples. Okay, so this is our main result. This is what I'm going to talk about. And to introduce and sort of justify why why did we pick the hypergraphs that we picked, we do need to see the characterization of Reiher, Rödl and Schacht, and more generally, we need to answer a certain question. So because we are looking for what is the largest quasi-random hypergraph that does not contain H as a subgraph, if we want to answer this question, we need some way to generate quasi-random graphs. So how do we generate them? Well, maybe just from looking at the word quasi-random, maybe the first thing that comes to mind is, let's take G and P. Well, then yes, if you do that with high probability, whatever you generate will be quasi-random. The problem is that we will also, well, if the density is positive, but the problem is that with high probability you will also contain arbitrarily large clicks. And no, the method of alterations is not going to save you. So then we need something else, some other construction. Okay, we had this construction by Erdős and Heinel with the tournaments, but that seems like a bit of a one-of-a-kind construction. Some clever idea just to show, oh, how nice this construction is. We need something that is easier to generalize. And this, so what was introduced for this was something called coloring schemes, or Reiher calls them palettes. I'm going to call them coloring schemes. So what is a coloring scheme? A coloring scheme consists of a set of colors and a set of ordered triples of colors from our list. So here, for example, I have a coloring scheme which has 3 colors, red, blue, and green, and 4 ordered triples of colors. And then how do you use a coloring scheme to generate a quasi-random hypergraph? So the first thing that we are going to do is going to be to color, to take the vertices from 1 to n, and here it is relevant that these are labeled vertices which come with a certain ordering. And what we are going to do is we are going to take the complete 2 uniform graph on these vertices, and we are going to randomly color it with colors from our set. And then for any triple of vertices, we are going to say that the first, the 2 smallest vertices, we are going to call those the left pair. The smallest and largest, we are going to call the top pair, and the 2 largest, we are going to call the right pair. And then for any triple of vertices, what you are going to do is you are going to look for at the left color, the top color, and the right color. And if those 3 form one of the ordered triples in your list, then you place an edge there, otherwise you don't. So for example, here in the vertices 1, 2, and 6, you see that the left color is red, the top color is blue, and the right color is green. And red, blue, green is one of the ordered triples in our list. Whereas for the vertices 2, 3, and 6, the left color is blue, the top color is green, and the right color is red. And blue, green, red is not one of the ordered triples in our list, and therefore we don't place an edge there. And here there's a definition that I haven't written in the slides, but it's important to say. We are going to say that a hypergraph admits a coloring scheme if it appears in some graph that can be generated using that coloring scheme. And if that happens, then with high probability, H will appear it will appear with high probability in a large enough graph generated by the coloring scheme. So Reiher, Rödl, and Schacht characterized that the vanishable hypergraphs, the hypergraphs which have uniform Turán density equal to 0, are precisely those which admit what I'm going to call the trivial coloring scheme or the vanishing coloring scheme, which is just one which has only one triple, which is made of different colors. So this means that a hypergraph has uniform Turán density 0 if and only if there exists some ordering of the vertices and some coloring of the pairs of vertices in such a way that in any edge out of the 3 vertices that form any of the edges, in that ordering, the left pair is red, the top pair is green, and the right pair is blue. So then, with this in mind, how is this useful to us? How do we look for these hypergraphs which have uniform Turán density equal to 1/27? Well, let's restrict our scope. Instead of looking at the family of all quasi-random hypergraphs, let's only look at those which are generated by coloring schemes. And let's ask there, what is the answer? What is the maximum density what is the density that already forces H to appear as a subgraph? There was some, I didn't mention, but if you generate a hypergraph with a coloring scheme, then with high probability it is quasi-random, and the density that you are going to achieve is just the the expected value that you get just from linearity of expectation. So in coloring schemes, is there something that happens at density 1/27? Is there some threshold, some property that forces if you take a coloring scheme that has density greater than 1/27? Well, yes, there is something that's sort of easy to see. If you have a coloring scheme with density greater than 1/27, then there must be some color that plays two different roles out of left, top, and right. So there must be some color that is the left color in some triple and the top color in some triple. Maybe it's in the same triple, maybe it's in a different triple, or maybe there's some color that appears as left in one triple and as top also somewhere, or some color that appears as top and as right. But there must be some color that appears in two different positions in some triple. And here the 1/27 is sharp because the trivial coloring scheme, if you only have one triple that contains three different colors, that has density equal to 1/27, and each color only plays one role. So then we must find a way to use this information, about a threshold occurring at 1/27, and the implication is that if you have some hypergraph H0 that admits these two coloring schemes, and these two coloring schemes are the ones that have two triples which only share one color, and in the first one the shared color is the left color in one of the triples and the right color in the other, and in the other case it's the left color in one of the triples and the top color in the other. And the third case in which you would have top and right is equivalent to this one, just reversing the ordering of the vertices. But if you have some hypergraph H0 which admits these two coloring schemes, then in fact it will admit every coloring scheme that has density greater than 1/27. And then if in addition it does not admit this one, then in fact the largest coloring scheme that H0 does not admit has density precisely 1/27. And so with coloring schemes, this is easy. This is like, if we are restricted to the universe of coloring schemes, then this is like very easy to prove. This is less than one page. The question is whether this still holds if we go back to the universe of all quasi-random hypergraphs. So we can hope that that is still the case, and indeed we proved that this is the case. Of course, we are not done yet with proving the main theorem. We still need to prove that such hypergraphs exist. But now that we have such a characterization, one can just check by computer whether and look for hypergraphs that have this property, and indeed you start finding them precisely at 7 vertices. And at 7 vertices, in fact, there are 9 of them. So suddenly at 7 vertices, you start finding many of them. So here is an example, one that has 7 vertices and 9 edges. And you can see that it admits these two coloring schemes. So you can see, for example, let's pick, for example, the edge BCF. So in the left, we said BCF. So F is less than B is less than C. So FB is the left pair, and you can see that it's in red. FC is the top pair, and you can see that it's in blue. And BC is the right pair, and you can see that it's in green. And red, blue, green is one of the triples in our coloring scheme. Whereas in this other coloring scheme, we have B less than F less than C, and BF is now the left pair, and it's red. BC is the top and it's blue, and FC is the right pair and it's green. And right, blue, green is still one of the triples in our coloring scheme. So it does admit these two coloring schemes. Of course, we also need to check that it does not admit the trivial coloring scheme to show that it is not vanishable. Well, this is a small example. We can just check by computer that it doesn't admit this coloring scheme. But because we are going to show that there are infinitely many minimal examples of hypergraphs with density 1/27, we are going to need some method that is better than just checking by computer. So here is an observation about the two drawings that I made, the two coloring schemes. So you might notice that even though the colors are different, they are not very different. In the sense that, well, of course, the yellow and the pink flipped with each other, but let's look at the red, blue, and green edges. So you might observe that the red graph did not change. The red edges on the left are also red in the right. And the blue and the green edges switched. So what's blue on the left is green in the right, and what's green on the left is blue on the right. That's not a coincidence. That's there is a deeper reason for why this is happening, and this has to do with the following observation. So let's suppose that our hypergraph H is vanishable. So there is some ordering of the vertices and some coloring of the triples in which all the left pairs are red, all the top pairs are blue, and all the right pairs are green. And suppose that we have two edges that share two vertices, so WXY and XYZ. If we know the relative order of these three vertices, let's say W is less than X and less than Y, then the pair XY will be the top pair, sorry, it will be the right pair in this edge, meaning that it will be a green pair. But then it will also be the green pair in the edge X, Y, and Z, so we know that Z is the smallest vertex. And because we still know that X is less than Y, then we have completed the ordering of the three vertices. Z must be less than X and less than Y. So if you have that the colors of this edge look like this, then in the other edge, it must be like reflected along the common pair. And that means that if we fix the relative order of the three vertices in one of the edges, then that information propagates along all other edges that share two vertices with it. So you can see this as propagating along the line graph if you take adjacencies to be sharing two vertices. So this is useful for our infinite family of examples, which looks like this. We are going to take three tight paths of equal length, and we are going to identify the endpoints. On one side, we are going to identify the endpoints equally, so A with A and B with B. And on the other side, we are going to identify them cyclically. So C with C, D with D, and E with E. Then let's suppose, for the sake of contradiction, let's suppose that this hypergraph is vanishable. And let's fix the order of the three vertices in the first edge of the first path. Well, because of the property that I showed before, the order of these three vertices also forces the relative order of the three vertices in the second edge. And that forces the relative order of the three vertices in the third edge, and so on and so on. The information propagates, and it ends up telling us out of C and D, which one is larger. So let's suppose for a second that C is less than D. Well, then the first edge of the first path also shares two vertices with the first edge in the second path. So that information also propagates along the second path. And if C is less than D, it will tell us that D is less than E. And propagating along the third path, it will tell us that vertex E is less than vertex C, and that creates a contradiction. So that means that this hypergraph here is not vanishable. And on the other hand, you can show that you can give an explicit ordering and an explicit coloring of the pairs such that it does admit these two coloring schemes, the two that are quasi vanishable, like the ones that have two pairs with only one coloring common. Okay, so this is our infinite family of examples, and I guess that for now I should tell you some words about how to prove this statement, how to prove that if you admit these two coloring schemes, then you appear in all quasi-random hypergraphs with density greater than 1/27. So it's a bit complicated to it's not something that I really want to give you to really introduce everything that goes into the proof, because even though it is not a complicated proof, it takes a bit to set up why whatever I'm going to show you implies the result about three uniform hypergraphs. Let me just tell you that there is an ingredient of hypergraph regularity, and that once you apply regularity because your graph was quasi-random, your reduced graph has a special shape, and which is approximated by something called that we call the n-partitioned hypergraphs. So when I say an n-partitioned hypergraph, this is going to be a hypergraph whose vertex set is partitioned, but not into n parts, but into n choose 2 parts, each of which will contain 2 different indices. And then we are going to say that it has density at least D if for every triple of indices, the induced tripartite hypergraph on Vij, Vik, and Vjk has density at least D. So you are only required to see edges precisely on the triples whose subindices match 2 by 2. And then Reiher, Rödl and Schacht, they were the first ones to use these partitioned hypergraphs in uniform Turán, and they proved that their characterization of vanishable hypergraphs was equivalent to the following property of n-partitioned hypergraphs. So if you have some positive density D and you have little n, and then you take your big N to be much, much larger than the previous 2, then in a big N partitioned hypergraph, it is possible to select a subset of your indices with little n indices. And then whenever you see a vertex set with 2 of those indices, it is possible to select there a red vertex, a green vertex, and a blue vertex in such a way that for every triple of indices, the red vertex corresponding to the left pair, the green vertex corresponding to the top pair, and the blue vertex corresponding to the right pair form an edge in your hypergraph, in your partitioned hypergraph. So here, for example, you can see that we restricted ourselves to the subset of indices 1, 3, 7, 8. And then, for example, between 1, 7, 1, 8, and 7, 8, the red vertex in 1, 7, because this is the left pair, the green vertex in 1, 8, corresponding to the top pair, and the blue vertex in 7, 8, corresponding to the right pair, those form an edge in our hypergraph. So this is equivalent to their characterization of vanishable hypergraphs. We are going to do something similar, but we need to do something a bit different. Because we are going to talk about the threshold that occurs at density 1/27, we are going to require to have n-partition hypergraphs which have density at least some constant greater than 1/27. And we are going to, instead of finding three vertices, 3 colored vertices, we are going to find 5 colored vertices. And that's because we are looking at coloring schemes that use 5 colors each. And the property that we are going to require is that for every triple of vertices, we are always going to find an edge formed by the red vertex in the left pair, the green vertex in the top pair, and the blue vertex in the right pair, just as in the proof of Reiher, Rödl and Schacht. But we are also going to look at to require that we find another triple that can be one of either pink, yellow, red, in which case the common color is left and right, or pink, red, yellow, in which case the common color is left and top, or pink, blue, yellow, in which case the common color is right and top. When we are proving this, and now it stops being equivalent because now we have forced the order of the vertices. So we cannot just say, oh, take the reverse of all the vertices. But other than that, the property is still the same, that we are required to find a subset of the indices, and we are required to find these 5 colored vertices only on the vertex sets that have 2 of the indices that we selected. And as for how to prove this, I'm just going to say that, okay, so Reiher, Rödl and Schacht proved this using some iterative approach. So they define some like sort of algorithmically. They selected the vertices, whereas we have done this using Ramsey's theorem. It is equivalent in a certain sense, in this meaning that we can write their proof also using Ramsey's theorem. And we apply it 7 times. So first, what we do is for every triple of indices, we look at how many vertices in those parts have a certain degree as the left vertex, a certain degree as the top vertex, and a certain degree as the right vertex. And then we apply Ramsey's theorem to make sure that all triples of indices have roughly similar densities. Then once we have that, because the density is above this 1/27, that means that there must be some vertices that play 2 different roles. Some vertices that are the left vertex in some triples and the top vertex in others, or some vertex that are left in some triples and right in others, or the top vertex in some triples and right in others. And then the second application of Ramsey's theorem goes into the quadruples of indices. And this actually quadruples, no, 5 tuples of indices. And it makes sure that all the intersections that we see are all of the same type. So in this application is where we decide whether we are always going to find the first type of edge, or we are always going to find the second type of edge or the third type. But once we have this, we can just apply Ramsey's theorem 5 more times, and in each of the applications, we are going to define the colored vertex for one of the colors. The first one that we select is always the intersection color, the one that must appear in the 2 triples, and then we select the other 2. So that's basically the broad idea of the proof. Okay, so I'm actually going to not to end the talk about here. So let me leave you with an open question. So as I mentioned, we found these hypergraphs with density 1/27 by finding some characterization in coloring schemes. And from this characterization, it follows very easily, like it is almost trivial to say that the densest coloring scheme that does not contain H will have density equal to 1/27. So the question in this restricted universe of coloring schemes was almost trivial, whereas proving this for the more general universe of quasi-random hypergraphs, proving that the uniform Turán density was equal to 1/27 for those same hypergraphs was by comparison much harder. So wouldn't it be nice if this was in fact just the same question? Wouldn't it be nice if just looking at the question in coloring scheme was coloring schemes was enough to determine what the uniform Turán density is? And in fact, Reiher asked this question, whether for every hypergraph, just looking at, in order to determine the uniform Turán density, it's just enough to look at which coloring schemes do not contain H as a subgraph. And it's not just our question that that would become much easier. So I can tell you, for example, that for the case of computing the uniform Turán density of cycles, so it had been known for a while that the densest coloring scheme that avoids cycles of length that's not for every cycle for every cycle whose length is not a multiple of 3, the densest coloring scheme that does not generate that cycle has density 4/27, other than the 4 cycle. But turning this question into uniform Turán density, showing that the uniform Turán density of cycles was 4/27 took a lot more. So as I mentioned, this question, if solved, it would help a lot with the analysis of uniform Turán density. And I do think that it should be feasible to tackle in and of itself. I do think that I do have like some statements that do not relate to uniform Turán density, which would imply this question, like in the phrasing of these reduced hypergraph. N-partitioned hypergraphs. So with this, that's going to be the end of the talk. So thank you for having me here, and thank you for your attention.
Thank you. And I would invite anyone to unmute their microphones and give Ander a round of applause. So are there any questions? So let me ask this. So you have this set of Turán densities, possible Turán densities. So what is known about that, beyond the value 1/27?
So for the uniform Turán densities, so I do expect, I don't know if much is known of what happens beyond 1/27. I do expect that 1/27 is also a discrete value, and that there is some jump after that. However, I know that in the usual, in the standard Turán density of 3 uniform hypergraphs, that there it is known that the value does not always jump, that there is some dense interval or something like that, that there are some other accumulation points that are not 0 or 1, and some places where the value just does not jump. So maybe the same happens for uniform Turán. I'm not going to I'm not going to speculate because I don't know where this where the non-jumping proof comes from, but maybe the same thing happens in uniform Turán. So I am reading now András's question. What was involved in setting up and solving the underlying constraint satisfaction problem? And do we have guarantees that the result does not omit any cases? So all we did actually was just check that. I mean, just look for hypergraphs that admit the two coloring schemes that that we have there, and not the trivial coloring schemes. And once the computer has generated that, then one can check by hand that those hypergraphs that are generated satisfy the properties. And in fact, we had the base cases. So the first case of the 3-path construction, we had that before we checked by computer the rest of the case to see whether there was any smaller example.
So maybe one question which could have been hidden in your explanations of these coloring schemes, and I just didn't get it. How specific is this whole concept of coloring schemes to the setting of this uniform Turán densities, of this uniformity assumption?
So there is a survey by Reiher on similar problems where you have different quasi-randomness conditions, where you impose quasi-randomness. So this would be just this would be actually equivalent to asking that if you have three sets of vertices of linear size, then the number of edges that you see in the tripartite graph that it induces is roughly the density times the product of the sizes. So there's other conditions based on whether you fix just a vertex, some vertex set and some set of pairs of vertices, or some two different sets. No, not two different sets, but like some sets of pairs of vertices, and then you have to see so that you have every edge contains a cherry in that set. You have some conditions like that, and Reiher gives some restrictions on the palette on this idea of coloring schemes on the palettes. Some conditions that are sort of that adapt to each of the definitions of quasi-randomness. But outside of uniform Turán density, I don't know if it has been if these coloring schemes have been looked at, or even if they have any application. That I do not know about them.